Let's talk about the area between two curves. We have a theorem that will tell us how to find the area between two curves. And let me pause for a second to draw a quick picture so that you can make sense of this theorem more easily. So I'm just going to pause this video for a second. Okay, and we're back. So suddenly you see that I've drawn this graph over here. Feel free to pause the video and replicate this graph if you need to on your paper. But what we have is we have f and g are continuous functions so that f of x is bigger than or equal to g of x over an interval ab. So here you can see I have an interval ab. My f is the y values of the f function are clearly larger than the y values of the g function on this interval. And what we're going to do is we're going to let r to denote the region bounded above by the graph of f of x and below by the graph of g of x. So we're talking about this region right here. So maybe I should take my highlighter and let me just color in the region that we're looking at. And this region right here is what this theorem is calling R. Okay. And it's bounded on the left and the right by the lines x equal to a, so that's going to be a vertical line here, and x equal to b, that's a vertical line there. All right. Then the area of R is going to be given by an integral. So the area in this case that's of R is equal to the integral. We're going to integrate from a to b, and we're going to have f of x minus g of x dx. So I guess the key thing to remember is that the bigger function is on the left and the smaller function is on the right. All right. Why don't we take a look at an example together? Let's take a look at example 1. In example 1, we have a region bounded above by the graph f of x equal to x plus 4. So I definitely want to sketch a graph of this. So let me draw a set of axes here. A set of axes over here like this. And I'm going to label the x-axis 1, 2, 3, 4 like this. I'm going to label the y-axis. I'm going to have 1, 2, 3, 4 like that. And when I look at this object right here, this f of x, this is a line, right? It's y is equal to x plus 4. So that's a slope of line equal to 1. I'm sorry, a slope of 1 and a y-intercept of 4. So, this graph probably looks something along the lines of this. It's not to scale, that's just a rough sketch, okay? And then it's bounded below by the graph of this function. Now this function is also a line. This function is has a slope of -1/2 and a y-intercept of 3. So again, this is just a sketch just to help us get an idea what the picture looks like. But that's the y-intercept there. And this maybe comes like this, something like this. So I can label this. This is g of x equal to 3 minus x over 2. And this is f of x equal to x plus 4. So I have my region of integration is from 1 to 4. So I'm going to put like little left boundary there and a little right boundary over here. And we're really trying to find this area shaded right here. So just to give you a visual for what we're doing. Okay. So this situation exactly mirrors the situation described on our theorem up above. So our area is going to be the integral from 1 to 4. The bigger function is x plus 4, so I'll put that function there. And the smaller function is 3 minus x over 2. And we're going to integrate with respect to x, so I put a dx like this. Great. So what I'm going to do now is I'm just going to evaluate this integral. So I think the first thing I should do is I should distribute the negative. So this will be the integral from 1 to 4. We're going to have x plus 4 minus 3 plus x over 2 dx. And then I'm going to combine like terms. So when I combine like terms, I'm going to get the integral from 1 to 4. This is the x terms combined to give me 3 halves x, and the constant terms combined to give me plus 1 dx like this. And then I am going to find the antiderivative. Okay, so to find the antiderivative of that first term, I could use a constant multiple rule. So the 3 halves is going to stay there. I'm going to add 1 to the exponent, which is going to give me a x squared. I'm going to divide by what I just wrote. So I'm going to divide by 2 like this. For the second term, the antiderivative of 1 is just x. And because this is a definite integral, I'm going to put a vertical line. I'm going to go from 1 to 4 like that. All right. So let me simplify this a little bit. This is going to give me 3 over 4x squared plus x evaluated from 1 to 4. I'm going to plug in a 4 there. That's going to give me a 3 over 4 times 16 plus 4. That's what I get when I plug in the 4. I'm going to put that in parentheses, minus, now I'm going to plug in a 1. I'm going to get 3 over 4 for the first term. I'm going to get plus 1 for the second term. When we simplify this, we are going to get 57 over 4 units squared. So the units for area are the square units, because if you think about it, you're like multiplying a length times a width. Okay, so I'm going to highlight this. It's my final answer, and we will continue this on another video. Take care, everyone.